Hey students, welcome back. This is our bell ringer. This should be your second bell ringer on that page. This is continuing with dilution, so please hit pause and meet me down below. Okay, so this week we're going to talk about definitions of acids and bases. So we're shifting our gear from solutions and now we're going to talk about acids and bases. So we're first starting with our definition of acids and bases. So there are actually officially three definitions of acids and bases, but we're going to only cover two in this class, all right? So our earliest definition of an acid was the Arrhenius definition of an acid. Arrhenius actually did a lot of work with solutions. He's actually the guy that termed or coined the term electrolytes and non-electrolytes, but the Arrhenius acid is one that produces H plus in solution. So that means when we put it into solution, it produces H pluses. All right. So his definition of a base was that it produces OH minuses in solution. And that actually worked for a few years, but then they had to kind of expand it out and continue it just a little bit. And that's where Bronsted-Lowry comes in. The Bronsted-Lowry theory now changes, and we don't talk about it so much in terms of H's and OH's, but the Bronsted-Lowry says that an acid donates a proton. All right. And the proton here, or always, will be H plus. So we're talking about donating a proton or donating an H plus. So it gives it away. All right. It will be losing an H plus. A Bronsted-Lowry base, here's where the definition changes. A Bronsted-Lowry base is one that accepts a proton. So we kind of have to see what is happening in our chemical reaction to see if it is donating or accepting. Some other words that we have here. Our first one is a conjugate acid. A conjugate acid is one, we're going to call it the former base, or yes, it was the base, and it accepted, it's the thing that accepted the H plus. All right, so this is the one on the product side. So these guys, these conjugate acid, conjugate base, are found on the product side of the reactant or the right-hand side of the arrow. All right, so the conjugate acid was the base. It's the one that accepted the H plus. All right, then we have our conjugate base. You guessed it, it was the acid, and it's the one that gave up the H plus. So it's the one that gave up the H plus. All right. And then we have a conjugate acid base pair. These only differ by an H. So they only differ by an H plus. So the only way to change it is it has an H plus difference. You either add an H plus or you take away an H plus. And that makes it a conjugate acid base pair. And then we have another word. We have amphoteric. Ampho, just like amphibian, means that it can act as an acid or a base. Ooh, that's not or. All right. Just like an amphibian can live on land or in water, amphoteric means it can act as an acid or a base, basically give up a proton or accept a proton. Okay, so let's see if we can do a little work here and kind of see, this is what our homework's going to look a little bit alike. So it says, what are the conjugate acids of the following? And our goal here is we're going to add an H plus. So all we're going to do is add an H plus to this, and we have to keep track of charges as well. But first, let's add the H part. So if I add an H to this, all I'm going to do is add an H to that, which gives me H2O. Now, if we look at our charges, we have a negative and a positive, right? Negative and a positive, so we have a neutral substance now. Okay, awesome. Let's see what happens here. Again, we're going to add an H plus. All right, maybe I'll put the plus on there so it's not confusing. So we're going to get H2CO3, and our charge on this one is also neutral. So maybe not our best examples since all of them are neutral, but let's kind of keep looking here. Now, our conjugate base, this time we're shifting gears. We've got a conjugate base, all right, conjugate base, and that means we're going to take away an H plus, all right? So conjugate base, we're going to subtract out an H plus. So if I take away an H from here, remove an H plus, we're going to be down to H2O. All right, H2O. We're taking away an H plus, so that plus goes away because of that plus right there. All right, let's look at that next one. Again, we're taking away an H plus. So now we're going to have CO3 because we removed an H. And now instead of this, we took away a positive and we had a negative already. So now we're down to -2. That's our charges there. Okay, awesome. Notice how we had to check our charges. And last but not least, it says, in the following reaction, it says identify the acid, the base, the conjugate acid, the conjugate base, and the conjugate acid base pairs. So there's a lot to do there. So let's first identify our acid and our base. Remember, these are going to be reactants. All right, these are going to be on the reactant side. Okay, these guys are going to be on the product side. And then the conjugate acid base pair, we'll get there in a second. All right, so let's follow the path of the H here. So maybe I can highlight. So HF becomes F minus. All right, notice how it loses that H. So the thing that lost the H is my acid. It donated the H. It gave it up. All right, the other one then has to be the base because if you see over here, it accepted an H. It added to it. So looking back at our definitions, the conjugate acid was the base. It's the one that accepted the H plus. So this is my conjugate acid, and this is going to be my conjugate base because it's the one that gave up the H. Now our conjugate acid base pair, you're just going to connect with lines. And remember, they only differ by an H plus. So there, ooh, that was unfortunate. Let's try that again. All right, they only differ by an H plus. Notice how HF and F minus only differ by an H plus, just like H2O and H3O plus only differ by an H plus. So that is our conjugate acid base pairs. All right, see you in the next video.